Okay, the thing I wanted to check out was this thing with the question marks around it, and it was wrong. It was P, V, P inverse. But the representation of V with respect to B is just P inverse P. There are a lot of ways to see that, but of course we developed it, where P is the matrix that has the basis vectors in its columns. It turns out that for an orthonormal basis, the inverse of P is just its transpose. Now, I didn't mention this in class. It's worth making a little note of. And it's very easy to see why. Okay, here's your P matrix. The vectors are in the columns. Now, if you do the transpose, those vectors will make up the rows. If you multiply the transpose then times the matrix, your first row will be the row consisting of the components of V1, and V1 over here will be the column. You'll be multiplying the V1 row by the V1 column. That is, you're going to be doing the dot product of V1 with V1, and you're going to get 1 since V is a unit, V1 is a unit vector. Then if you do the first row times the second column, you're dotting V1 with V2, and that's going to be 0 because these are orthogonal. And then V1 dotted with V3 essentially, and again 0 because V1 and V3 are orthogonal. If you go to the second row, well, you multiply, that's the V2 as a row, multiply that by V1 as a column, that's a dot product of V2 with V1, it's 0. V2 dot V2 is 1, etc. You're going to get the identity matrix, and it's really easy to see why. And what I've written here was the way a transformation would be expressed, okay, not a vector. So I just wrote that down very carelessly. So this is what you do. So we could multiply the inverse of this, which is the transpose, by this vector, and we would get the components of the vector, okay, relative to B. And that's exactly what we would get. This is exactly what we would get if we did that. Now I'm going to approach this from a little different perspective, though. And these commas almost look like subscripts, so let's make them look, now they look like 9s, but okay, we'll live with it. In any case, very simple thing. And I just actually proved it with what I said. If you have an orthonormal basis, then any vector relative to the standard basis is expressed relative to the orthonormal basis in this way. So here's your vector V. We do V1 dot V, that's the first component. V2 dot V is the second, V3 dot V is the third. Now the way we can understand that too is that V1 dot V is the scalar projection of V1 of V on V1, provided V1 is a unit vector. Okay, so these are scalar projections. I didn't write all the words. Maybe I didn't put an arrow over projection, so implicitly that's a scalar projection. But I'll write the word scalar over each of these. You probably can't read it. I can't even read that one. Okay, but in any case, V1 dot V is a scalar projection of V onto V1. Okay, your picture is here. Here's your V vector. Here's your V1 vector. I don't mention the angle theta. We haven't even calculated it, but we could. Here's the vector projection. The scalar projection is then the length of this vector projection, and it's positive in this case. If the vectors were like this, the scalar projection would be back here. The vector projection would be back here, and the scalar projection would be negative, being in the direction opposite the V1 vector. So we regard that as The first component of V, second component of V, third component of V. The component of V relative to the V1 direction, the component of V in the V2 direction, the component of V in the V3 direction. These are the components of V. Here, they're calculated. Now I just did the dot product of this with this, the dot product of this with this, the dot product of this with this. I got 3 dot products, okay? This one, and this one. Each one has an X1, an X2, and an X3, okay? Because of course you're dotting this with this, and you have the number in front of it. Very simple calculation. And I expand just a little bit. V1, I say V1 dot, okay, I'll say the magnitude of V dot V1 is the magnitude of the projection of V1 onto V. Because why? Because V1, V dot V1, that's whatever. V dot V1, well, the projection of V onto V1 is V dot V1 over magnitude of V1. Again, that just corresponds to this little triangle. And this is the scalar projection. And then multiplied by the V1 vector divided by its magnitude. Well, what's the magnitude of the V1 vector? This is an orthonormal basis. V1 has magnitude 1. So we have 1s for both of these denominators. So this just becomes V dot V1 multiplied by the V1 vector. And the magnitude of that is the magnitude of V dot V1. Now, if you just do V dot V1, this thing here, that's the scalar projection, and remember it can be positive or negative. So that justifies this interpretation.